So welcome everybody to today's webinar about using clustering to compute the properties of fluids. And this we are doing this by heavy use of Mathematica's built-in graph theory capabilities. But before we start with the physics and the mathematics, let me shortly introduce me. So I'm 𝗪𝗲𝗯𝗶. I'm working at 𝗪𝗲𝗯𝗶. So we are a small company based in Berg, Upper Austria, and we develop software with for simulation and data science projects with industry and finance companies. And we are also reseller of Wolfram technologies, and which Mathematica is a product of. And it's the company behind is Wolfram Research, and is based in the US, in Champaign, and was founded in 1987 by Stephen Wolfram. And they have other products, so Mathematica is, so to say, the flagship, but they have other products in their portfolio. So, for example, Wolfram Cloud, Wolfram Alpha, System Modeler, and Wolfram Language. So with this, we can start with the physics. So here's a short abstract. I won't go into details. You can read it afterwards. So the talk will be made available in the Wolfram Cloud. And so what we want to do now is making this connection from starting from an atomistic picture. So for example, an atom or a molecule, and I use water because it's an example which everybody knows and is familiar with. And water, we know, consists of water molecules, which are one oxygen atom and two hydrogen atoms. And this is the molecular structure. But if we put more of these molecules together, we see that it's not simply a certain number of molecules, which we have to describe individually. There is some complex behavior appearing or emergent behavior. And this is what we mean by this quote, more is different, which is a quote of Phil Anderson, a famous physicist. And if we put more of these molecules together, we see all the properties we know from water. So it's fluid in a wide range with a lot of properties, a lot of special properties, and below 0 degrees it becomes solid, and above 100 degrees it starts to boil, and also some other special features. But all these features have the origin in this structure of the sample molecule, and the difficulty is to make the connection from this molecule to the complex behavior we see in our everyday life. So, and the way how we can do this is more or less known. So it's a part of physics. It's called statistical mechanics. And as it's often in physics, although we know how we can go from or can formulate the problem in a certain form of equation, it's difficult to solve this equation. So this is known from quantum mechanics. The Schrödinger equation you can write down, and it looks very nice. But if you want to solve it for a few particles, it becomes intractable. And it's similar also in classical physics for the statistical mechanics. And I want to I provide here the formulas. You don't have to know the statistical mechanics. I show you the formula and the mathematical problem. And from this formula, we will simplify and try to solve with Mathematica. So, and one way to write this problem, or part of this problem, is the virial expansion. And this is to describe the fluid properties is the equation of state is one way to describe it, or the virial expansion. And this is nothing else that we can calculate the pressure depending on the temperature. So this is the Boltzmann constant, here the temperature, and the volume. So here's the partial derivative with respect to the volume of the logarithm of some quantity, which is depending on the particle number. And this quantity here is the canonical partition function. So, and the complexity of this expression here, so these are only prefactors, the complexity is hidden behind this symbol here, and this is the configuration integral. So, and again, we can split this in its contributions. So this Vn is the interaction energy, and if we have a pair interaction, which is a good approximation for most of the particles, we can calculate the interaction energy by summing all possible pair interactions. So we can rewrite this configuration integral in this form. So it's a double product of this two particle interaction, and this is further separated because most of the time the interaction becomes zero when you separate the particles far apart, and then this function here becomes 1. And in order to separate this function in a trivial part, so this is 1, and the short range part f, which is called the cluster function. So we have this is simply a function of distance, and we can insert this in this expression here, and this is the mathematical problem we have to solve. So we have an integral over all particles and of all pairs of particles. So, and this is done by indicated by this double product. So, and you can imagine that this becomes quite complicated for a reasonable number of particles. So a reasonable number of particles, we talk about 10 to the 23 particles. So, but let's start smaller. So let's look how this expression looks for if we have only, for example, 4 particles. So we take n here, we define n to be 4 and evaluate this double sum here. And it's not too complicated, but if we expand the product, so it's still a product here, okay, this becomes a lot of terms and a little bit untractable. So, and this is only for 4 particles, and if we go higher, it becomes even worse quite fast. So what we can do to simplify this, so one way is to use graphs, and these graphs have built in Mathematica and nicely have nice functionality which represent this mathematical expression quite nice. So what is a graph? In Mathematica, it's simply a collection of undirected edges in its basic representation. So we have here 2 undirected edges, so connecting 1 and 2 and 1 and 3. And this is the argument of the graph. And what we have is, so the undirected edge is represented by this line here, and these are the nodes, which are, so this is 1 here, 2 and 3. Well, actually, it doesn't matter. So they had done usually not explicitly labeled because the node 2 and 3 can be interchanged. Whether this is 2 or 3 doesn't matter. This will become important later. So enter undirected edges directly, so then it looks like this, or by this escape sequence. So a little bit more information can be given to the graph. So if usually we can only give the undirected edges here, a list of undirected edges, or supply a list of nodes in the first argument, and then the list of undirected edges connecting these nodes, or not, as you can see already here in this example. So we have here these 3 undirected edges connecting 1, 2, 2, 3, and 3, 1, but we have given 4 nodes, and we see that this node 4 is not touched by the by the edges. But this is also a valid graph, and this also appears in our integrals, what we see later. Okay. So what we have to do, we have to translate our expression. So we have to replace our cluster function by the undirected edge, and the integrals become these nodes or vertices. So, and this we can pack into a function. So here we again define our contribution to Zn. So these are again all these diagrams we have seen before, or all these terms we've seen before, and now we want to make it a diagram. And this is done by this function here. So this function, we can give an expression, and it transforms this into a diagram. So we replace this f cluster functions by undirected edges and specify the nodes, and this gives them the graph. So we have an example here. So let's look at this third diagram in this expression above. So it's simply the cluster function connecting 1 and 3, and in the integral this means so the contribution to Z4 is exactly this, and we apply this to the function, and we see that we are connecting 1 and 3, and here nodes untouched 2 and 4. And also other diagrams are simply converted, or other expressions are converted to diagrams. So, and we not only doing this for one single diagrams, we want to do this for all. So we take these all diagrams, make the summary list, and then apply the transformation from which makes our diagrams to all the elements in the list, and again apply the plus on the resulting list. And what we get is the transformation of the expression above, which was looking quite complicated here and intractable. And so here, these are all diagrams contributing to this. And they are quite a lot, but we see immediately some structure here and some ideas how to simplify it became immediately visible, because here these diagrams looking identical, and we can combine them because they are indeed they have the same number and can be combined in one diagram with a prefactor. But as we see, this is already quite long. So these are 64 diagrams, and by collecting these, combining these together, we can simplify this. And going to the next order would become already quite messy. So we have then over 1,000 terms in the sum, and going even higher will be even more cumbersome. So, as indicated already, we want to sum these identical diagrams, and this we are doing in two steps. So we delete the duplicated diagrams, and then count the number of diagrams in one class. So we have to define two functions here. One is the count function. So we this function here counts how often a certain graph. So I can give here a graph, and how often this graph appears in a list given here, the graph list. And this is quite simple. So we can test whether a graph is identical to a graph in the graph list by the isomorphic graph question. And this gives true if they are isomorphic, and we are counting these graphs together. So we define this function here, and then we sum all together and get a number. So, and this is the function with what collects all this together. So we first generate all diagrams or all terms to these diagrams, and then make it a list, sort this list, and apply our graph function. So we make this list as a list of graphs. Then we delete, as said before, the identical diagrams by applying this function, delete duplicates, which is built in Mathematica by the test whether a graph is isomorphic to another one. And what is isomorphic? I've shown you before. If it's drawn in a similar way, or it can be drawn in an equivalent way, it's isomorphic, and then it's deleted, and then from this reduced list, we count how often every diagram in this reduced list is appearing in the full list. So this is the full graph list, and multiply this weight. So in the reduced list, multiply each diagram with the weight of this list. It's a little bit complicated, but if we evaluate it, we will immediately see what's happening. So every diagram which appears several times before is now collected or summed up, and we see, okay, this diagram, what was appearing several times, so it was appearing 6 times, and we have summed it up in this expression. And now we have only a few diagrams left, which we have to sum. So this is quite nice now, but still a lot of diagrams to calculate, and we are only at 4 still. So 4 particles. So, and to make further progress, we first need to get a little bit more complex. And this is by introducing this grand partition function. And this is taking the z function from before, but now summing from 0 to infinity. So in principle, for all possible particle numbers, and each contribution is divided by 1 over this n factorial, the number of particles. And this z star is nearly the same as before. The only thing that changes is that this activity function is connected with every coordinate. But otherwise, it's the same. This is only a small change. And this activity function is nothing else than the exponential of the chemical potential and an external potential. But we don't need this external potential here, but it can be generalized, and you can do much more different things than we do here now. So this does, by doing this, we don't have to change too much in our function. We simply say, okay, we have now the vertex, which was before gray, is now has a different meaning here, and this we symbolize by a different color of the vertex, and we make it simply black. And the prefactor has to change because we have to divide by 1 over n factorial. So this is the function as defined above, so this get expression. But what changed is that here we are dividing by this n factorial, and so the weight is divided by n factorial, and the vertex style is black. And we choose now a different embedding of this graphs to, and in that way it's a little bit nicer drawn in lower order. So otherwise it's nearly the same as above. So we can evaluate this function, and we can see what changes in this expression. So diagrams are the same, but now a little bit differently drawn, and the prefactor is now divided by 4 factorial. So 4 factorial should be 24. So we have 1 over 24 here, and 6 over 24 is 1 over 4, I think. Yeah. And so on. So it's not much changed here. And we can now look at different orders, because we have now only 4 particles, and we now want to sum all possible particles numbers from 0 to infinity. This is quite difficult, one might think, or impossible to do, but let's look here at the first 4 orders. And what we see here is that, okay, the first order is trivial. It's simply the integral over the coordinate. And the second, we have the first non-trivial part here. So this cluster function appearing here. And when we go to even higher, always this function again appears. So we also have it here and here twice, the same function. And if you write down the integral, like above, you will see that this can be separated into. So we don't have to calculate make the integral of these 4 coordinates. We simply can calculate this diagram here, and this one here is simply the square. So it's the same value here, and because it's in this under this product, it's simply the square of this first diagram. And this we can use to make things more simple. So we want to get rid of these disconnected diagrams. This is the task of this slide here. And this will make things much more simpler in this calculation. So we define here a function which gives us the prefect of a diagram. So before we had to do all the sum, and I simply use some graph theory to get this prefactor. Not to do, have to always calculate all possible diagrams, then throw most of them away, and to get the prefactor, I can do this with this function too. And if we compare with above, we have seen the prefactor of this diagram was 1/24, and the one of this was 1/8. We can check whether this is true. So this was 1/24, this was 1/8. So this function indeed calculates the prefactor of the diagrams. So then the next thing was, we have seen that if we have diagrams which are disconnected, they simply the value of one diagram. So if we have 3 times disconnected here, it's simply the value of this diagram. So we can evaluate that this gives a number, but this number to the power of 3. We don't have to do this integral here. And the same is true for multiplying different types of diagrams together. So Mathematica don't know this here. So we can put a diagram to the power of 3, but it cannot evaluate it. So it's the same. And to make them mathematically aware of this, we redefine the power function for graphs. So this is this function here. If we have a graph to the power of something, it's simply a graph disjoint union. So we are connecting this graph, and it can now evaluate this expression here. So we see that this is equivalent. So this to the power of 3 is equivalent to this, and Mathematica knows now this. The same thing, or a similar thing, can be done with the times function. And so if we multiply one graph by another graph, and which is nothing, disappears in the natural evaluation of this set factors, it becomes a combined graph. So this is now one graph, and so we can deal with this in a mathematical way. So next we go to this. So we want to demonstrate how we can eliminate all these disconnected diagrams. And for this, we are looking at what are the prefactors of these diagrams to higher orders. So we have here a list where we go to higher orders of these types of diagrams, and we get calculate the prefactor of this. And yeah, we see here it's becoming quite small if you go to higher order, but that's how it is. And this maybe somehow reminds of the series expansion of the exponential, but not really. So there's something missing still. So what we have to see this, that these can be mapped in some exponential function. We now take this series expansion of the exponential and replace x by the first diagram in the where this simple connected line is appearing. And this is, so this diagram, and it's appearing in the lowest order with a factor 1/2. And so we are doing this. And since Mathematica is now aware of this power function, it directly evaluates it. And we see that indeed the prefactors of the individual diagrams are identical. So take here the last one. So we have here 5 times this connection. So the prefactor is 1/3840. And if we apply this series expansion, we get the same prefactor, 3840 for this diagram. So this is quite impressive and nice, because we can now, in principle, calculate all diagrams to infinite order. If we put this diagram here in the exponent of the exponential function of the Euler number. And the same is not only true for identical diagrams. We could now use this series expansion. So this is the series expansion of the exponential here. And now we replace not only by this simple function, we replace it also by the simple dot and the first three node diagram. And we can evaluate this. This is now again because we know that Mathematica now knows how to deal with the power and times function with different diagrams. All types of diagrams are calculated here with a certain prefactor. And we can now check whether the prefactor is correct here. So we take some diagrams. So I took this one here and evaluate this, and we indeed get the same prefactor as we get if we put this in the exponential. And this is also true for others. So we can also take this one. And indeed the same prefactor. So this is really verifying that this can be done. So this can be rigorously proven and has been done in former times. And you might imagine that this is some work to prove this mathematically, but here we see it by manipulating some basic mathematical algebra. Okay, we have to take time here in order to that the later things don't become take too long, because it always tries to do some multiplication with this, or to use this combination of graphs. So we I cleared the times function again. So, but what is important here of this, what we have seen here before, is that we instead of summing all kind of diagrams where all these disconnected diagrams appear in order to calculate this function, we simply can calculate all connected Z diagrams and put it in the exponent of the Euler function or the Euler number, and get all possible disconnected combinations of these diagrams immediately. And so we indeed make an approximation to the calculation of this quantity to infinite order. This is quite a massive resolution and a very nice computational result. So to get this now in our function, which before we have calculated the all kind of diagrams, so we included the disconnected, we now modify the function from before and only keep the connected diagrams, which makes it again simpler. So we redefine this function. So, and here we get the connected diagrams which we have to put in the exponential of this function, and these are now even less. So we are not yet finished with some derivations. Afterwards, we'll really do the calculation for argon, but first we calculate something else in order to get our pressure virial expansion. So because now we have some good approximation for this computational function, we can calculate other properties, and one is the density. And the density is defined as the functional derivative of this computational function with respect to the ZR factor. And in this way, and here's this prefactor, you can rewrite this a little bit, and we actually need the functional derivative of the logarithm of this computational function. So really only the connected diagrams are appearing here. So, and in order to do this functional derivative, this is nothing else than in every diagram replacing each closed node, each black node, and open it, making it a wide open node, which means that we have now a function that is dependent on R, because the density depends on the coordinate. And so this is now an external coordinate in this graph. And we can define this functional derivative in a graphical way. And the main thing here is to have this graph automorphism group, and this gives us all possible group orbits, and with this we can calculate the weight of the derivative. So it's a little bit confusing if you want. It takes some time to understand what's happening here, but it's not too complicated. So the derivative, calculating the derivative of this diagram means we have to take the sum of all possible opening of black dots. So we have to open this black dot plus this plus this plus this, and only one in each time. And then we see that we can again sum identical diagrams, and we see that this type of diagram is appearing 2 times, because whether I take the functional derivative with respect to this node or to this node doesn't matter, because this is symmetric, and we can sum them, and it gives us a 2 as prefactor. And if we take the derivative with respect to this node or to this node or to this node, gives also the same diagram, and so we can sum them, and we get a prefactor of 3 here. So this is the functional derivative of this diagram. And here's another example. So this is done all automatically by this function. And so we have the functional derivative. We can now redefine this and give the connected, calculate the connected density. And let's have a look at this, how it looks. So we have here the external point here appearing R, and the cluster functions connecting these 2 points here, which have to be integrated. And here it's the open point is here, and it is here. So we can do this for certain orders, and we see that certain diagrams appear here, and we can again reduce these doubly connected. We can reduce certain classes of diagrams which are appearing here. So again, if the open point here is an articulation point, like in this function here, or in this function, which means articulation points, if I remove open this diagram at this point, the diagram separates in two parts. So there's this part here and this part. And if this can happen like this, or the diagram is like this, you can see that if the system is homogeneous, the two diagrams are simply multiplied by each other. And since they are multiplied by each other, it's like the disconnected diagram, and we can apply the same trick as before for the disconnected diagram, and we can resum certain classes of diagrams. And the second point is not, so this is an articulation point, but this point is also an articulation point, and we can reduce also the appearance of this articulation points by making a topological reduction. I will show it briefly here. Graphically, it's like playing playing with Lego bricks. So this is a diagram that can be topologically reduced. So here's this articulation point, and we can split this integral if we open here the point and make the integral explicit. And this is nothing else than the multiplication from before. And we see that this is again a diagram appearing in the expansion of ρ itself. And we can get rid of all these articulation points by replacing in this cluster expansion the set factors by density factors. And so we again introduce a new type of vertex, which is now a brown vertex, which indicates that we do not integrate over Z, we rather integrate over the density here. So, and what is the result? Is that we can express the density divided by Z by the sum of all double connected row diagrams in the exponent here. And this we put in a Mathematica function, which we call get log density of a certain order, and we can calculate this log density for some arbitrary order. So the only limit is the computation time, so it becomes quite heavy for higher orders, but in principle we can do this for all orders. And the first contribution here is the second diagram, and this is this diagram. And we can up to 4 or even 5, it's no problem. And these are these diagrams. This we will calculate later explicitly. So here's again summarizing. If we have a gray dot, we simply integrate over the coordinate. Brown means over the density in the coordinate, and black over Z and the coordinate. So with this, we are nearly done. So there's some short physical derivation to get the Wirbel expansion. One can follow this if one wants, or look up in the book. The result is, nevertheless, we get the pressure as a function of the density and a temperature. So this is the density here, as the sum of from 2 to infinity of this get log density with this prefactor here. So with this we have solved this problem. We only need to calculate now the integrals, which can become troublesome if we go to higher order. But the lowest orders can be done easily, and we see how it will perform for argon. So now we do actually what they've shown now in all this derivation. We apply this to a real atom or real substance, and this is argon here. So argon is a noble gas. It's used for some technical applications, for welding, for example, or some other things. It can be compressed and liquefied below 150 degree Kelvin. This is the critical point, and even if further compressed and cooled down, it can be solidified. And so this experimental findings, and this can be collected in or approximated in the van der Waals equation of state. So this is a phenomenological equation. So it tells us how this macroscopic fluid, macroscopic substance, argon behaves in a certain range. It doesn't describe solidification, but it describes the liquid and gas phase transition. This can be seen here. So what we are plotting here is the van der Waals equation of state. So this is the blue line, and comparing it to the ideal gas, which is the trivial solution. So if we neglect all correlations or interactions, we get the ideal gas. And here we have a manipulate plot, and we see we are immediately here at the critical point. So we have here the temperature 150 degree Kelvin. So it's minus 120, I think. And the critical point means we have a negative slope appearing below these temperatures here. So if we go to higher temperature, we see this function becomes closer to the ideal gas, and this slope becomes larger, the minimum slope, or we don't have a minimum in the function here. And going below 150, a minimum is appearing here. This means we have a phase transition from gas. So this is the ideal gaseous argon, and then it becomes liquid in this state below a certain volume. This can be seen by the Maxwell construction. So the Maxwell construction says we have here equal areas, and compressing the gas from large volumes to smaller volumes, it will start to condense at this point. If you further decrease the volume, the pressure remains constant, and even more, even a larger fraction of the gas liquefies until this point. And here everything is liquefied, and if all the argon is liquefied, or the gas in the general case. So for argon, it's argon. So this we would have here. So it starts liquefying here, and here it's all liquefied. So this is what we can see from the experiment in the macroscopic picture. But what we know from the atom picture, so argon can be, the interaction between two argon atoms is well described by Lennard-Jones potential. So this is represented by this function here. So this is the interaction potential of argon. The Lennard-Jones potential is a 1 over r to the power of 12 minus 1 over r to the power of 6 with some prefactors. And we can plot this here. And this is the interaction potential in terms of Kelvin. So Kelvin is here used as an energy unit. And the distance here is angstroms. So we have a minimum at about 4 angstroms, and then the potential disappears for a larger separation. And this means for the cluster function we defined before, so it's the exponential of the interaction potential divided by the temperature minus 1, and this looks like this. So it's behaves very well. So it starts at minus 1, has some peak here, and then disappears above 10 angstrom. That's it. So we don't have to integrate to very large separations because this function disappears. This is why we did all this cluster expansion. Okay, so this is the atom, and now we want to apply our derivations or the result of our derivations to make this connection from the atomic picture to the macroscopic picture. This is only to define. So B is now giving the prefactor of the virial expansion. So what we had before. So we have this get log density function, and we start with the second order correction. So calculate what is the contribution to this second order. So this is the diagram which has an external point here R. Here this point here is integrated over 2 and minus. This is the value of this correction factor. So now we have to transform this diagram back to an integral. So we have the prefactor, you have this integral 1 over minus 1 half. And integrate now this function, this cluster function. So this is this ft here. And because we're in a homogeneous system, the point r can be chosen arbitrary. So we choose 0 here and integrate over this point in all space. And because it's radial symmetric, we can do a radial integral. And so the x here is the radius, and we integrate over the spheres. So this integration can be done immediately analytically, and we only have to do the numeric integral from the radius 0 to 6 sigma, which is more than enough to have a convergent integral. And this is only for the units. So these are for the angstroms, because we have an integral to d r3, so x, y, z, and that's because we have here this correction for this unit factor to transform angstroms to meter. So this integral is very simple and fast to calculate in Mathematica, so we can do it on the fly. And this is the result. So for 160 degrees, it's a little bit small here, but this is 160, so above the critical point, we have this. This was what the experiment is telling us. This is the ideal gas, and our correction gives us brings us to the green line here. And we see that for large volumes, we are nearly on top of the experiment. So we are very well describing what's happening here. But as we go to higher densities and close to the critical point, of course, we start to deviate, and it becomes negative here. And we are not able to capture this phase transition at all, because there's no branch here going to an up here. So even if we go down, it becomes even worse. And at higher temperatures, it's not too bad. It becomes even better. So this is 200 degree Kelvin. This is quite good. So, but we can do better. So this was the second order. Let's go to the third order correction. So what diagrams we have to calculate? So this is this one. This is already a little bit more complicated and takes a little bit, not too long, but I won't do this on the fly, so I do the calculation for this diagram here. So it was about 1 second, and this is the result. So how we transform it, let's first look at this. So again, we choose here 0 as the coordinate r, and then integrate. So over this is x, this distance here, and this distance here is y, and this distance here between these 2 points can then be calculated by the cosine proof. So it's this function here, and entering all these integration parts, we can simply numerically integrate this and get the value for this correction factor, and this is this. So we put this in our plot here. So here we have again the van der Waals result. So this is the first plot. This is the blue line again, and then the ideal gas is always the second. So this is this here, and this is the second correction. So B2 funct, this was from before. This is the green, and now we have the third order correction. This is this one here, and we see this is this red line here, and it's improving the approximation in this regime here, and going to even higher densities. We see that it correctly predicts already a phase transition, but at a much too high temperature. So it would predict it at, I don't much above 150 degrees. But at least it can predict the phase transition, so it's not completely unphysical, the behavior at small, at high densities here. And we can do even better if we go to the fourth order. So these are now 4 diagrams, and the first 3 are rather straightforward to calculate, and the third one is the one that takes the most time. And I show here how you can do it, and it takes about 20 minutes. So this is the integral, and I used the other adaptive Monte Carlo method to calculate it and get the value, and taking the values for all the rest of these diagrams. I have done in a separate notebook, but it's not difficult to do this here. And this is the value. You can again do the same plot as before. And we see that now this is the purple line here, and we are still slightly deviating, but not correctly not predicting a phase transition at 160 degree. So if I go down at 155 degree, there will be we will predict with this fourth order the phase transition, but this is also already quite close to 150 where it's appearing in reality. And for such a rather simple, no, it's not simple, but numerically it's not as tedious as a Monte Carlo calculation if one has tried this before, or molecular dynamics, because we have here doing this one calculation gives us a complete range of this function with respect to the volume. And at another temperature, we again have to do the calculation for this complete range. We immediately have this complete range as result. So the fifth order I didn't do, but we can look how the diagrams would look like. We have to calculate. So these first few are rather simple, and the tricky part one will be this one. But I don't have done it yet. So with this, I want to summarize the talk. So I hope I could show you that with this symbolic computational capabilities, we can speed up the complex physical derivation and make the derivation more transparent. So it's I understand it's a little bit fast and complicated in this talk, but otherwise I think you have to take much more hours to understand what's happening here, and with this you can more easily follow. So I think the derivation become much more transparent. And the other thing, at the end, we had a simple function which can be published. So I can publish it somewhere, and you can use it whenever you want. And want to say, okay, I want to calculate the 6th order, you can do it if you want. So you get the diagrams, and then you know what to do. Otherwise, computing these diagrams is quite a messy derivation, as there are quite a lot of them. So, and we have shown that this gives good results already for argon up to 4th order. So as outlook, so these calculations, some of these calculations can be done much more efficient, and even we could go to much more accuracy if we include the Baire density and some other classes of diagrams, which are called this hypernetic chain diagrams. And funny, so actually I'm coming in my PhD, I worked on and postdoc, I worked on Poisson and Fermi liquids, and there one can also rely on this methods. So we can calculate quantum liquids with these kind of methods, and which cannot be done with Monte Carlo, for example. And one nice thing would be to apply this formalism to Feynman diagrams. So here we deal with this undirected edges, but Mathematica supports also this directed edges, and this would be exchange lines in Feynman diagrams. And so one could generalize this formalism, I think, to Feynman diagrams too. This would be a funny work. So here are some references I mentioned before. For example, this Hanson McDonald is a nice reference where some of the work showed here has been presented. And with this, I want to thank you for your attention. So so I thank you for your attention, and also my co-workers and Unisoftware Plus for supporting the work.